It's the early 2010s. Android phones are being launched. Humanity witnesses the new pattern locks for the first time. It's a culmination of engineering, art, and security. Everyone is loving it. Actually, I don't know because I use PIN numbers, but anyway. Somewhere, an edgy teen wonders, how do I look the most cool while unlocking my phone? Somewhere else, a secret agent asks, how can I have the maximum security for my lock pattern? Mathematicians begin to seek the ultimate answer to all the questions. What is the most complicated lock pattern? Before we start, there are 4 rules in Android lock patterns. 1. A pattern cannot use a dot more than once. 2. A pattern should use at least 4 dots. 3. Order matters. This and this are 2 different patterns. 4. You can skip dots. For example, I'll start from top left and connect directly to top right. But as you can see, the pattern also includes the middle dot. However, if you have already used the middle dot before, then it's possible to directly connect. How complex a pattern looks is really subjective, so we can't just call a pattern the most complex if we don't have a definition. In our problem, we define a pattern with maximum complexity like this. First, the pattern must use all 9 of the dots. Pretty simple, more dots, more complexity. But of course, that isn't enough. Look at this pattern and this one. Why does the second one look more complex? One possible answer is that the second pattern has more types of lines. So a line between 2 dots can have various slopes. There's the horizontal line, the vertical line, 2 45-degree lines, and so on. There are 8 different lines in total. Now, if we look at the first pattern, it only uses a disappointing 2 kinds of lines. But if we look at the second pattern, it utilizes 7 different types of lines. So that is going to be our second criterion for complexity. The more types of lines, the more complex. If there's a pattern using all 8 different lines, that would be the most complex pattern. If there are multiple solutions, then those will all have the maximum complexity. This is what we are going to find. Now, you might be wondering, is this a serious video? Yes. Look at the length. This is my math explainer as a submission to the Someone event. Actually, this might not even be qualified because of the length, but I'm just fully committed. And to prove how serious I am, I prepared an extremely formal mathematical definition of our problem. First, let's examine if the most complex pattern actually exists. Let's name the 8 different types of lines according to their slope. The horizontal line would be slope 0, this line would be slope half, and so on. The vertical line technically doesn't have a slope, but let's call it slope infinity for convenience. Let's also name the dots 1 to 9, starting from the top left. Our pattern will go through all 9 dots, which means there will be 8 line segments connecting them. Since there are 8 types of line slopes, this means that each slope must be only used once. That's a pretty tight condition, so can a pattern actually use all 8 of them? Let's try making one. My first gut sense is that these weird lines would be hard to handle, so we could try using them first. I'll start from dot 1, go 8, 3, then 4, 9, then maybe 6, and 2. And now I've arrived at a dead end. I cannot go to 5 because I've already used slope infinity, and I cannot go to 7 because I've already used slope 2. I could keep trying with other dots until I find one, or dump the job on you. Throughout this video, there will be some questions provided to you. You may pause and try it yourself or just skip it. Our first problem is, try to create a pattern with all 8 different line slopes, so a max complexity pattern. At this point, we don't even know if it exists or not, but just try it for a bit. It's a fun puzzle. So, did you find one? The answer to the existence of a max complexity pattern is yes, it does exist. Actually, the pattern in the thumbnail is a valid answer. This was the first solution I found when I tried this puzzle back in high school. The pattern starts from dot 1 and goes 8, 3, 5, 2, 6, 7, 9, 4. I didn't have any deep logic while finding it, it was just trial and error. So, we found a max complexity pattern pretty quickly. Is this the end? No, our career as lock pattern researchers has just begun, and we can't just stop at one. Of course, we have to find all the solutions. Maybe there is a formula that can calculate the number of max complexity patterns. Or even better, maybe there is a formula that exactly tells us which patterns have max complexity. However, this approach is quickly met by a wall. There's most likely no easier way to calculate the number of max complexity patterns than just finding them one by one. Why? To answer that, let's just look at a less complex problem. How many smartphone lock patterns are there in general? No conditions whatsoever, just the total numbers. If you Google it, you'll find that the answer is this. How was this calculated? By brute forcing a program to count them one by one. In fact, this problem alone is too complex mainly because of the no skipping rule, and using formulas to count is very impractical. Now, our problem is slightly more complicated than this. Is brute forcing the only way possible? We would have to find, presumably, tiny amounts of max complexity patterns among hundreds of thousands of patterns. But this doesn't mean that we need to find them blindly without any discipline. We can make a logical procedure to find them. And to help that, I present another problem to you. Try to find another max complexity pattern without any trial and error. I will give you the first two dots of the pattern, which are dots 1 and 2. There is only one solution to this problem, and there is only one logical path to take in each step. Here's the solution. We started from dot 1 and came to 2. Here's a list of slopes that we need to use. Now watch the slope minus 2. This slope can only be in two places, but the left case can never happen in our pattern because dot 1 is already used. That means if we are going to include this slope, it has to be the right case. And since we are already in dot 2, we know that the next dot has to be dot 9. The same can be done afterwards. Watch the slope minus half. The only place left for it is the lower position, and we need to go to dot 4 if we are going to include it. Next, we need to use the slope minus 1, then slope 2, then infinity, then half, and the final slope left is conveniently the one we can use. With this method, we can find all of the max complexity patterns. Suppose we're in the middle of drawing a pattern. We must first check if there's a slope that needs to be used right now. If so, use that slope. If not, just use any slope that hasn't been used. We can repeat this process. If we end up with a valid pattern, add that to our list of solutions. If we reach a dead end, meaning all the options need a slope that's already been used, then we retreat and continue with a different path. With this method, and sheer willpower as a professional lock patternologist, I found all of the max complexity patterns by hand, which is 296. Please don't do this and just use code. If we ignore the rotating and flipping, there are 37 unique patterns that I will show right now in one glorious list. There are 11 patterns that start from the corner, 19 that start from the edge, and 7 that start from the middle. 21 of them, when drawn, goes over one of the 9 dots multiple times. Oh, look at this one. It has a little star. Actually, a lot of these have little stars. These two have the most number of polygons in it, which is 11. Anyway, we found all the max complexity patterns. Now that you've come this far, I'd like to share a bit of context how this topic came to be. I'm an undergraduate in Korea. This was my topic for a math report in my second year of high school. It was one of the most stressful moments, grades, preparing for college, and this was like a little rebellion. This wasn't even done for a school project at first. I just tried that first puzzle and got interested afterwards. That's why this was such a memorable moment in my high school years. So, thanks to someone and the people there for making me get this video out. Thanks for watching, and now that we've found all of the most complicated lock patterns, our journey ends here. Except there's so much more time left in this video. Frankly, a 3x3 pattern is not that secure as a lock. Now we're on the cutting edge of lock patternology, and we could open a new horizon. What about patterns in a 4x4 grid? What about a 5x5? What about a rectangular grid? Does a max complexity pattern even exist? How many are there? We need to generalize. First, let's look at the number of slopes for different grids. A 2x2 grid is the simplest case. It has 4 different slopes: 0, infinity, 1, and -1. That's bad news because there are also 4 dots. A pattern using 4 dots can only have 3 lines, so it's impossible to use all 4 slopes in a pattern. So, according to our definition, a max complexity pattern does not exist in a 2x2 grid. How about a 4x4? First, there's slope 0 and infinity. Next, we have the positive slopes, which can be neatly shown starting from the lower left corner, and there are 7 of them. The number of negative slopes is equal to the positive ones, so in total, there are 16 slopes. Again, a max complexity pattern is impossible. We need the number of slopes to be less than the number of dots. Things change in a 5x5 grid. There are 11 positive slopes, so the total number of slopes is 24. That's exactly 1 less than the number of dots, so this time it's theoretically possible. Well, we don't know for sure until we actually find a pattern, but at least we know it's not downright impossible. So, 2x2 is impossible, 3x3 is okay, 4x4 is impossible, 5x5 is okay. Do we see a pattern here? Looks like if the grid size is odd, it's okay. Here are the number of slopes for some rectangular grids, and it seems to follow this pattern. There are less slopes in dots if both x and y are odd. Perhaps this will be true for all sizes of grids, but of course it's not that easy. The rule we just found is totally wrong for larger grids. For example, a 9x9 grid has 88 different slopes, which is 7 more than the number of dots. So we're stuck at another wall. The problem is more complicated than we thought. What should we do now? There is only one solution: dump the problem on you. Right now, we only knew the number of slopes by counting them one by one. Try to find a more mathematical way to express the number of slopes. Maybe drawing that grid on an xy plane so that the slopes actually have mathematical meaning. You can technically solve this only using high school math, but it could be hard, so I wrote a big hint in the description. So, the answer is simple. All you have to do is make use of the summation of Euler's phi function. Wait, it's still possible to solve with simple terms. Euler's phi function isn't really needed, okay? Watch this. First, the total number of slopes is equal to the number of positive slopes times 2 plus 2. Next, all the positive slopes can be counted simply by starting from the lower left corner. This is because no matter what line you draw, if it has a positive slope, you can move it so it starts from that corner. Now, let's look at all the positive slopes in a 5x5 grid. We will draw an xy plane so that the lower left point is at 0, 0. Now, the position of each dot directly relates to the slope of the line. This line has slope 1 over 2, so the position of the dot is 2, 1. This line has slope 3, which is just 3 over 1, so the position of the dot is 1, 3. Now let's look at dots that didn't get connected to a line. Why did the dot 4, 2 not get a line? It's because that line just has a same slope as this line. 2 divided by 4 is just 1 divided by 2. That dot didn't get a line because we could reduce the fraction. On the other hand, all the dots that got a line have fractions that cannot be reduced further. There are no common divisors of its x and y coordinates, or in other words, x and y are coprime. The number of positive slopes in a 5x5 grid is equal to the number of points where x and y are coprimes. And of course, x and y are limited to be less than 5 because that's the size of our grid. To get the number of all slopes, we just have to multiply this by 2 and add 2. This time, it actually generalizes to all grids, and we have our formula. By coprime point, I mean a point whose x and y are coprime. See, we didn't even need the summation of Euler's phi function. You may argue that this doesn't really give a concrete formula to calculate the number of slopes, that we just redefined the problem in a more technical way. But you see, that was the point all along. Since coprimes are such a popular topic in math, there are tons of theorems found by people. And if you just Google a bit, you can find formulas like this. And I'm going to copy the heck out of it. I will try to prove this in the next chapter, but it's a bit hard, so right now let's take it as granted. So now we know that the number of slopes in an n by n grid is larger or equal to this. Let's compare that to the number of dots, which is n squared. If we graph the two functions, we can see that they meet somewhere around 11. And after that, the pi squared thing is always above n squared. Since the number of slopes is even larger than the pi squared thing, we can say, without doubt, that all grids larger than 11 by 11 have more slopes than dots. For grids smaller than 11 by 11, we can just check them one by one, and find that only 3 by 3, 5 by 5, and 7 by 7 grids have less slopes than dots. By the way, here's the actual number of slopes for all n by n grids. In the next chapter, we will prove the equation we saw before, and also calculate the number of slopes for rectangular grids. But this chapter contains more advanced number theory, so if you do not recognize either of these equations, you can skip the next chapter, or continue at your own risk. You could also watch this 3 blue 1 brown video beforehand, the link is in description. Welcome to the bonus chapter. As said before, we will try to prove this with some number theory. Are primes involved? Yes. Is the Basel problem involved? Yes. Do we get to use the summation of Euler's phi function? No, not really. But you have to know one thing before we start. Here are numbers from 1 to n. How many of these are divisible by 2? Well, about half of them. How many are divisible by 3? About a third of them. Now's the question. If we take away all the numbers divisible by 2, how many of the ones left are divisible by 3? Now, you might think, oh ho, this is a bit more complicated, but no. It's still just about a third of them. That's the thing about primes, they just kinda don't interact like that. A third of odd numbers are divisible by 3, and a third of even numbers are divisible by 3. Same thing goes for any other two primes. Now let's get to the problem. We have an m by n grid. Draw the x and y axes, and we'll now look at points 1, 1, 2, m-1, n-1. How many of them have x and y coprime? Since x and y are not coprime if they have a common divisor, we'll do this. Step 1. Let's count all the points. That would be m-1 times n-1. Step 2. We are going to remove all the dots that have a common prime divisor. So let's start by removing all dots whose x and y are both divisible by 2. About half of dots have x divisible by 2, and about half of dots have y divisible by 2. So about a quarter of dots needs to be removed. After removing, the number of dots left would be about 3/4 of the original dots. Next step, from the dots left, we remove all dots whose x and y are both divisible by 3. We can use the fact that primes just kinda don't interact. So about a third of dots left have x divisible by 3, and same for y. So about a ninth of dots needs to be removed. The number of dots left would be about 8/9 of the dots from the previous step. Next, we remove all dots whose x and y are both divisible by 5. We are basically going to do this for all prime numbers. And when we are done, we can safely say that the dots left have no common prime divisors between x and y. But the thing is, if we do this for all primes, we're kinda overkilling it. There are going to be lots of primes larger than the grid size, so that there are no dots in the grid whose x and y are both divisible by that prime number. And since we are multiplying all these fractions because we've accounted for them, the result on the right side ends up being a bit smaller than the number of coprime points. This is not a rigorous proof, but in essence, that is why the number of coprime points is larger than or equal to n-1 times m-1 times that thing. Now, what is that thing? This is nicely explained in this Mathologer video. It's actually easier to calculate the reciprocal of that thing. Let's split the fractions and look at each of them. Does this remind you of anything? That's right, we can use the geometric sum formula to rewrite this as 1 plus quarter squared and so on. Do this for all other prime squares, and we arrive at this monstrosity of an expression. But when we actually expand this, we get something nice. If we take all the ones, then we get 1. If we take 1/4 and then all the ones, we get that. If we take 1 and then 1/9 and then all the ones, we get this. If we take that one, which is 1/16, and then all the ones, we get this. And basically, we will get all the 1 over natural numbers squared exactly once. This is because every natural number is uniquely factorized into primes, so every squared natural number is uniquely factorized into squared primes. That sum is from the Basel problem, and it is pi squared over 6. All this means is that that thing from before is the reciprocal, 6 over pi squared. It's over now, the number of coprime points, which is the number of positive slopes if you recall, is larger than or equal to this. So the number of all slopes is this, which is definitely larger than 12 n-1 m-1 over pi squared. End of proof. Let's also briefly look at which rectangular grids have less number of slopes than dots. Number of slopes for an x by y grid is larger than this, and the number of dots is xy. Let's graph these two functions in 3D. This looks complicated, but in the end, we get that if a point xy is in this red region, there are definitely more slopes than dots. So we exclude all of them, and the only ones left are these. We can check them one by one. For x equals 6 to 10, we can just check all of them, and conclude that only 7 by 7 satisfies our condition. For x less than 6, we need a bit more thinking since there are infinite number of them, but it's not that hard, because the number of coprime points have a simple pattern if you limit them to x less than 6. For example, this is a 2x grid in the xy plane. Technically it's a k by 2, but it doesn't matter. And it's easy to count the number of coprime points, it's just k minus 1. Multiply by 2 and add 2, and the number of slopes is 2k, so not less than the number of dots. A 3x grid is also easy. All the points in the middle row are coprime, and all the points in the top row just alternate. Try finding the number of slopes, and you'll get that there are less slopes than dots only if k is odd. I'll skip the 4x and 5x grids, but if you calculate, the only grids with slopes less than dots are 5x5 and 5x7. Summary of what we did until now. We started from a puzzle without much logic. We introduced logic and built a procedure for solving similar puzzles. Then we generalized to find the potential candidates of grids that might have a max complexity pattern. Where can we go from here? I see two ways. One, we can just continue finding patterns in 5x5, 5x7, and 7x7. But this is just another brute force problem. Anyone could find them with some coding. For example, here's one I found in 5x5. But you see, looking at this doesn't really give you the same level of satisfaction when you first found a 3x3 pattern. On the other hand, we have this infinitely many 3 by odd number grids. Will all of these have a max complexity pattern? Now this is a completely different problem, and we can't just brute force because there's infinite of them. Very exciting, so we'll go this way. Let me tell you, I actually reached this point when I was doing this project in high school. Of course, I didn't know anything about the formulas from the last 2 chapters, but I somehow got that all the 3 by odd number grids have less slopes than dots. However, I was almost burnt out at this point. I was tired of counting patterns. Don't get me wrong, patterns are great, but the final exam for the semester was in 2 weeks and I was fed up by all the workbooks. And I was conflicted because, in a corner of my heart, I knew that I had to get an answer to complete my mission. As a cutting-edge pioneer of log patternology, I knew that finding all possible grids for a max complexity pattern would be a major breakthrough in the field. Should I try to solve this problem even though I don't know where to start? Is the time spent going to be worth it? I remembered a tale in The Alchemist by Paulo Coelho. A miner who came so close to finding emeralds after 5 years of mining. A higher being sees this and helps them remove the final stone. I don't know if miracles can happen, but they will only happen if I try. So I decided, let's just try a little bit more. Because, well, anything is more fun than studying in exam periods. Long story short, I put weeks into this nonsense and eventually found a solution. And it was a miraculous one too, because the solution literally involved the very first pattern I found. The trick was to extend this pattern. We add 3 dots to each side, and somehow extend the pattern to make a 3x5 max complexity pattern. Then we add 3 dots to each side again and extend the pattern in the same way into 3x7. In other words, we can create a formula that generates a max complexity pattern for any 3 by odd numbered grids. Now this is a very important part. Before I show you that formula, I want you to try finding it. I admit that this is harder than any of the problems before, but it's really worth it. You see, this video was structured so that it gets more and more mathy towards the end. One might think that more mathy only means more logic and calculations, but that's not always the case. When I first learned how to prove the formula of sum from 1 to n, it was weird because it looked like the question only made sense if you already knew the answer. How would you come up with this exact formula if you didn't know it? If you were finding the formula for the first time, I'd guess that it takes a lot of intuition and trial and error to find a formula that seemingly works, and only then would you try to prove it rigorously with mathematical induction. Solving our problem is one way to experience this process yourself. This last try it yourself is not that different from the first one. It's intuition and trial and error. It's only difficult because you need more understandings of the problem, such as the exact number of slopes for each grid. One method I recommend is to divide this pattern into a few parts, extend them individually, and add all the parts again to make a 3x5 pattern. For example, this X pattern on the bottom will be extended like this. That is all I have for the hints. Again, I really recommend trying this yourself. Induction problems using geometry like this are pretty rare. And now, the proof. What you just saw was a large portion of the proof done visually. We made a formula that generates max complexity patterns for all 3 by odd number grids. The difficulty of finding it may have been different from person to person, but I think it becomes a lot easier if you organize the slopes into groups. If you look at the hint, these are the slopes for each color. Organizing slopes of bigger grids, for example, these slopes from a 3 by 5 grid, may look like this. The groups are 1 over even numbers, 1 over odd numbers, 2 over odd numbers, and 0 and infinity. Trying to expand the pattern this way could have led to the answer. You still have to guess, but it's more of an educated guess. Also, we still have to prove that this formula is actually correct, but that can be done with a bit of logic. It's a matter of finding a way to expand the pattern. Again, what you're seeing on the screen is basically the proof, and I'll leave the stricter proof to you. This is just like completing the mathematical induction after finding out the formula of sum, and it brings an end to our journey. We can finally say that the most complicated patterns exist everywhere. So I guess the mental takeaway of this video would be this. Math involves lots of pesky calculations, but it's also based on intuition. But intuition is different from just making random guesses on a puzzle. How is it different? How would you explain the beauty of intuition? It's not quite like the perfect neatness of logic, but it still comes from some deep part of our complicated brains. You know what? The beauty of intuition is just like the beauty of complex patterns.